Welcome to Maths with EJD. In this video, we are continuing with mathematical induction, and the question we'll be taking here is this: prove by induction, that n into n plus 1 into n plus 2 is an integer multiple of 6 for all n is greater than or equal to 1. That is what we have to prove right here. And of course, we already have standard procedures for all these things. So the first one we want to do is to clearly state the claim. The claim here is that n into n plus 1, n into n plus 1 into n plus 2 is an integer multiple, of 6 for all n is greater than or equal to 1. So that's the claim. So the next thing to do is to think about the base step. The base step is where we test values like 1, 2, and all that. So let's do that here. So the base step. So for the base step, let's say at n equals 1, we don't need more than at n equals 1, but I like to do more than that. So at n equals 1 means we have 1 into 1 plus 1. That's n into n plus 1 into n plus 2. That's 1 plus 2 here. So that's 1 into 2 into 3, which is 6. And 6 is the same thing as 6 times 1. So 6 times 1 is a multiple of 6 as expected. Then I would like to take that further and say at n equals 2, that's 2 into 2 plus 1 into 2 plus 2, right? That is 2 into 3 into 4. That is 2 times 3, 6. 6 times 4 is 24. And of course, 24 is 6 times 4. So which is also a multiple of 6. So the base step is satisfied, the base step. So we can say, therefore, the claim is true. The claim is true for the base step. The claim is true for the base step. So now that we have taken care of the base step, we want to deal with the inductive hypothesis. So for the inductive hypothesis, what we simply do is to assume that the claim is true for n equals k, because that's the best we can do at that stage. So we assume that the claim is true for n equals k. That way, it means we are saying that k into k plus 1 into k plus 2 is equal to 6 times anything you choose. Let's say 6 times j, where j is an integer. That's very important. Where j is an integer. So that's all we can do at this stage. Now, we have to pay attention to this because it's going to be useful at the next stage, which is the inductive step. So for the inductive step now, what we simply do here is to prove the claim for n equals k plus 1. So we want to prove the claim for n equals k plus 1. So that means that for every k, right? Okay, we already know where we're coming from, right? That k into k plus 1, k into k plus 1 into k plus 2 is equal to 6j. Okay, we have that standing. So if we take it further, for n equals k plus 1 now, So it means we're going to have, for every k, we have k plus 1. So instead of k, we have k plus 1 into, for k plus 1, we have k plus 1 plus another 1. And here we have k plus 1 plus 2, okay? So instead of k in each case, you have k plus 1. And that means we have this to be equal to k plus 1 into k plus 1 plus 1 into k plus 1 plus 2, which is simply the same thing as k plus 1 into k plus 2 into k plus 3. So here we have to make a very smart move. And the smart move is I want to bring k plus 3 to the back because in the original expression, there was no k plus 3. So what if I bring k plus 3 to the back and I have k plus 3 into, into k plus 1 into k plus 2. That's like some kind of smart move. So I can at least have what I started with and something else which can be shown to be an integer of 6, an integer multiple of 6. So I can now say k multiplied by this whole thing, and I get k into k plus 1 into k plus 2. This has been established to be a multiple of 6, at least from where we are coming from the inductive hypothesis stage. So the next thing we have is 3 multiplied by this whole thing. That is plus 3 into k plus 1 into k plus 2. So without any doubts, from where we are coming from, we know this guy is 6j. Okay, so we can write that out. Uh, so we know this expression is already 6j, which is established as a multiple of 6. But this other one we have now is 3 into k plus 1 into k plus 2. So will this always be a multiple of 6? Can we do a few checks? Of course, we have established for 1 and 2, so we can go higher. Let's pick any random values. I'll just pick any random values. For instance, I have 3 into k plus 1 into k plus 2. In fact, what you already have here, so once you can have any of these to be even, then it's automatically correct that it is divisible by 6. You know why? Let's say at k equals, just pick any number, 5, So you have 3 into 5 plus 1, 6, into 5 plus 2, 7. So you already have 6 here. So this is divisible. Pick any other one, any random number again. Let's say k is 11, right? 11, anything. So you have 3 into 11 plus 1. Oh, well, I don't want to make it look like I'm picking I'm carefully selecting these numbers. Let me just pick, I just want to pick any number at all. Let's even say 20, let's say 22, right? Anything I pick, it will just work. So let me pick 27. Yeah, good. 27, right? So you have 3 into 27 plus 1, that's 28. And 27 plus 2, that's 29. I like this. Already you can see, you can break this down into 3 times 2 times 14 times 29. Okay? Because 28 is 2 times 14. So you already see the 6 coming out here. So whatever k you choose, as far as it is greater than or equal to 1, this expression will always be a multiple of 6 also. Okay? So we can simply see now that, okay, if you call this, you can also call it this 6 something. So this can be like 6j plus 6m, So this expression is like 6m, such that at the end of the day, you have 6 into j plus m. And it is clear already that uh, where j and m are integers. They are confirmed integers. From all that we have done, they are confirmed integers already because we assumed this, and then here, this is very sure to be an integer because you can factorize 6 out of, choose any number, you can always factorize 6 out of it. So with that, we have confidence that all the conditions have been satisfied. So we can reach a conclusion that uh, since the claim, of course, the claim is that n into n plus 1 into n plus 2 is a multiple integer of 6. Is a multiple, it's an integer multiple of 6 for all n greater than or equal to 1. So since the claim, of course, you know what the claim is, just like I just stated. Since the claim is true for the base step, for the base step and the inductive step and the inductive step and the inductive step, then it is true, for all what were we given? For all n greater than or equal to 1, for all n greater than or equal to 1. For all n greater than or equal to 1, that's for all positive integers, or for all integers greater than or equal to 1, basically. Okay. So with that, we have come to the end of that proof, and that's how it just goes. You need some critical thinking, just like you've been told in the introduction. And if you have not subscribed, be sure to do that. Hit the notification bell so you can always get alerted when a new video is released. And of course, you want to like, you want to share, you want to make comments, you want to request for problems you need solved, or particular topics you think I should treat in this series of videos. Thank you so much for listening. See you in the next video.